Here's the first one. It's called advection. What advection means, it's the displacements of gradients of a property by a flow. So you need a flow of a certain speed, plus you need a gradient of a property. And let's illustrate it here. It's a little sketch, and you can see that there is some patch of a property. Okay, and as you move that around in space, you actually move around gradient. And in a one-dimensional channel, this can be formulated by an equation. And this equation is shown here on this in this yellow box. And this is an equation. So let's activate the mouse. Okay, activate the mouse. And let's see what's written down here. So again, it's an equation. And it has two sides. You have a cause. The cause is on the right-hand side. And the response or the reaction is on the left-hand side. So let's check what's on the left-hand side. It says dc dt. This means how does the concentration change with time? Okay, how does it change over time? Well, it doesn't change if what's on the right-hand side is 0. Okay, on the right-hand side, there is a product. Okay, there is a u, and u is actually the one component of velocity. So it's the x component of velocity. It can be positive or it can be negative. This u. Okay, positive means the current is directed to the right, to the east. Negative means it's directed to. And the other part of the product is a spatial gradient of c. How does c change in the x direction? Okay. And only if you have a combination of a flow component and a gradient that's when you get an advective change. Okay, and it's also multiplied with a negative sign, and you understand that on the next slide. Okay? This is what we call advection. And how does it look like? Now, I'll give you one example. Okay? So this is one example. Okay. What you see here on this little diagram, this little sketch, is the distribution of C, of a concentration. Okay, and it's like a photo of this concentration distribution. Here you can see on one side of the channel there has a concentration of 1 or 100% if you like. And on the other side it has a concentration of 0. And there's a transition. There's a transition between the 1 and the 0. Okay, this is just a photo. Now you have to imagine that this entire shape is moving. Okay? It is advected by a current which has the speed of u. It's a positive, it moves to the right. Okay, it's illustrated by this arrow. So now this entire concept of advection only works at fixed location. Imagine you are at this fixed location here, marked by the star. You have a control volume here, and now you observe the changes that you get as this concentration field is moved past your location. So a long time nothing happens, because the 0, all that the flow does, it actually moves the concentration of 0 past your location, and you don't observe anything. You only observe the change as the flow moves this gradient, this change past your location. The change from 0 to 1 is a spatial gradient. This is where the dc dx is not 0. This is what you observe, and afterwards there is no more change because the concentration is at 100%. This is what we call advection. Advection is the movement of gradients of a property past a location. And this is what you observe. You only observe the changes of a property. There's no change. Okay? You observe nothing. So you get no advection in two instances. One, there is no flow, no movement at all. Means there will be no change. Or the property is uniform. The distribution is uniform. Then also there can be currents or so, but you don't observe any change. So this is what we call advection.